Welcome to lecture number 12 for EE206 Circuits 1, Superposition. Now, superposition uses the property of linearity. A circuit that's composed of resistors, inductors, capacitors, and voltage sources is a linear system. And linear systems have the property that f of a plus b is f of a plus f of b. What that means is that if you have a circuit with two or more inputs, the output is a function of those two inputs. A perfectly valid way to analyze it is treat that as two separate problems. A problem where you have the first input turned on, and a problem where you have the second input turned on. The sum of the two outputs will be the answer when they're both turned on. Now, this is extremely powerful when we get to AC analysis, but also applies to DC analysis. This will just look at the DC terms. For example, suppose I have the following circuit where I've got a 10-volt source and a 5-volt source, both powering the circuit. I can analyze this using voltage nodes. And with voltage nodes, what you do is write your 5 equations, 5 unknowns. That just be V0 is 10, V4 is 5, then at V1, the current left, down, and right as to 0, likewise at node 2 and node 3. That gives you 5 equations, 5 unknowns. And if you solve, you'll get V0 is 10, of course, V4 is 5, and the voltages V1 to V3 are something between 5 and 10. That's what we've been doing previously. There's a second way to solve. The second way would be use superposition. I'll first turn on the first input, 10 volts, turn off the second. That makes V0 10, V4 5, or V4 equal to 0. And now solve. Write the node equations just like we did before. Solve, and I'll wind up with 10, 8, 5.7, 3, and 0. That's the first step with superposition. Second step. I'll turn off the left source and turn on the right source. Now I've got voltages between 0 and 5 volts. And note that if I take those two, where the left input's turned on, then the right input's turned on, and I add the two together, that's your f of a plus f of b. I get f of a plus b. The sum of the two is the result when they're both turned on. That, in a nutshell, is superposition. If you have two or more inputs, I can treat them one at a time and solve the circuit. The total answer will be the sum of all the results for each of the separate inputs. Now, where this is useful in many places, especially when we get to AC. At DC, there's a couple circuits where this works really well. For example, this is an R2R ladder. This is used in embedded systems. It converts a binary voltage. Say if I have ABCD equal to 1, 0, 1, 1. Convert that binary number to an analog voltage. Now by superposition, I know that the output will be a linear combination of something times D, something times C, something times B, and something times A. So I know this is what the output's going to look like. This is a linear circuit, so it's got to be linear. To analyze, let's find each of these terms one at a time. The first one, to find A, I'll set D, C, and B equal to 0, A equal to 1. Nope. Now find the output Y. This is where Thevenins come into play. If I take this point X looking left, the Thevenin equivalent looking left is 2R, and parallel with 2R gives you R, and 0 volts. Now look left at Y. Looking left at Y, I see R plus the Thevenin R gives you 2R, and parallel with 2R gives you R. At Z, I see R plus R, 2R, and parallel with 2R gives you R. Now at the output, by voltage division, I just have Y, or 1 volt, going through 2R to ground. The output is 1/2 volt. So the scalar A is 1/2. Now let's look at B. I'll make the voltages 0, 0, 1, 0. Now find the output at Y. And just like before, this will give you R, combining R, combining R. The Thevenin equivalent looking left at Y will be 1/2 volt, and 2R in parallel with 2R, R. So I have 1/2 volt, R, R, 2R. By voltage division, I now have 1/2 of a half, 1/4 of a volt. So B is equal to 1/4. Now let's look at C. Take the Thevenin equivalent looking left, I see R. At X looking left, I see 1/2 volt and R. At Y looking left, I see 1/4 volt and R. At Z looking left, I see 1/8 volt and R. So the output is 1/8 volt. So the net result is Y is going to be 1/2 A plus 1/4 B plus 1/8 C plus 1/16 D, and so on. This converts a binary number, ABCD, into an analog voltage. And also note that the Thevenins make the analysis a lot easier. I could do voltage nodes, solve 4 equations, 4 unknowns. Thevenins are actually a much easier way to solve it. Third example, let's do a weighted average. Suppose I want to have the output Y being the weighted average of voltages A, B, and C. A couple ways to do that. First, let's start out with the simplest case. Suppose Y is just equal to the average of A, B, and C. In that case, by symmetry, I could just build this circuit, and by symmetry, Y will just be the average of A, B, and C. You can solve that using voltage nodes. If I write the node equation of Y, you get Y minus A over R plus Y minus B over R plus Y minus C over R equals 0. The R's cancel. I get 3Y is A plus B plus C, or Y is the average of A, B, and C. So that's the average where each has equal weighting. Next, suppose I want to have A with double weighting. Then what I could do is just have 2 resistors, A going through R and a second A going through R. R in parallel with R gives you R over 2. So this would have the weighted average of 2A plus B plus C. And note the weighting of 2 just makes this resistor half as big. In general, if I want to have a weighted average of A, B, and C, I would just pick a resistor R. This resistor is R over A, this one's R over B, R over C. I've got a weighted average. But note for this to work, the sum of the numerator, A, B, and C, is equal to the denominator. If they're all equal to 5 volts, Y will be 5 volts. Where this is useful. In computers, typically the output or the input to a D to A converter is 0 to 5 volts. If I have an analog signal that goes from minus 10 to plus 10 volts, and I want to convert it to 0 to 5 volts, that's just a weighted average. Here what I want to do is say the output is 1/4 of A. Again, A varies by 20 volts, minus 10 to plus 10. Y varies by 5, so the gain is 1/4. 20 volt spread going to 5 volt spread. Plus an offset when A is 0 at midband, Y is at midband, 2.5 volts. I can rewrite that. Suppose I have a 5 volt source and a ground source available. I could say that Y is 1/4 A plus 1/2 of 5 volts. That's the 5 volt source I'm assuming. And that doesn't quite work because I have a half plus a fourth. These don't add up to 1. I'm missing a fourth. So what I could say is plus 1/4 times 0. Now if I rewrite it in this way, I've got 3 input signals, A 5 volt source, and a ground. The weightings are 1, 2, and 1. So a circuit that does that is pick a resistor for A, 1/2 that resistance for 5 volts, and the resistance for 0 volts. This circuit will convert minus 10 to plus 10 volts to 0 to 5 volts. So that's lecture number 12 for EE206, Circuits 1, Superposition. If you have 3 different inputs, I can treat that as 3 separate problems. That's somewhat useful at DC. It'll be really, really useful when we get to AC analysis. So we're going to see superposition again. But the idea is if you have 3 inputs, you can treat that as 3 separate problems. That's a perfectly valid way to analyze the circuit. Lecture 12 for EE206, Circuits 1.